If I understand correctly, I will give the presentation, and if there are questions, they will be afterwards in the chat. Is that correct?
Yeah.
Okay.
Yeah. So yeah, I think questions are going to be asked by Soumik on behalf of students, and because like many students will be there, so like we are not going to allow all of them to ask a questions to you. So they'll type those questions in the chat box, and from the chat box, Soumik will select some questions. He will ask only those particular questions to you.
Okay, I understand. And the students are from different years of education, or are they all?
Yeah. The mostly master students only, masters and PhD students both. Yeah.
I understand. Good, excellent.
So Janaki, probably we can start now, or you want to?
Yeah, we can start because people join slowly. I think they are probably they are in still lunch break, so they will join slowly. Yeah.
But you would like me to start, or you would like me to wait?
No. I'll give some introduction, Kathrin.
Okay,
Then
wonderful.
after that, I'll ask you to join. Okay.
Okay, great.
Okay. Hello everyone. Welcome to the Department of Chemistry, IIT Delhi. Thank you very much for joining this webinar today. My name is Janikiram Vaitla, Assistant Professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is a part of the online Pratidhwani series that the department is organizing. Under Pratidhwani, we invite eminent scientists from the different areas of chemistry from all around the world. These 30-minute talks are held every Thursday afternoon. Please do check out our webinar website. You can find the link in our flyer emails and also on our department website. The webinar series is sponsored by OtherCafe. OtherCafe is an online platform that aids with writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with products like Mendeley, Zotero, Orchid, Crossref, and so on. Like Google Docs, special designed and developed for the academic community and much more. Before we start the webinar, a couple of technical details. Please do not unmute yourself during the talk. If you have any questions, please type them in the chat box and we will try to get at least some of them after the talk. Before we start the webinar, I would like to give a brief introduction about today's speaker, Professor Hopmann. Professor Hopmann received her PhD in computational chemistry from Royal Institute of Technology, Sweden. Before PhD, she worked as experimental chemist to investigate enzymes and proteins. And after her PhD, she worked as a postdoc as well as a researcher at University of Tromsø, Norway. Since 2014, she is leading her own research group, which is applying both experimental organic chemistry and theoretical quantum chemistry tools in the investigation and development of organometallic catalysts. Our current research project involves experimental and theoretical studies of transition metal catalyzed processes, including hydrogenation reactions using metals like iridium, cobalt, iron, and organometallic conversion of CO2 to higher value products. Currently, Professor Hopmann is a leader of NARD CO2 Consortium and coordinator of CO2 Parade ITN and also associate editor of organometallics. Today, Professor Hopmann is going to give a talk on computational catalysis applied to hydrogenation and carboxylation reactions. A very warm welcome and over to you, Kathrin.
Thank you very much for this really nice introduction. I'm very honored to be here today and present some of our work to you. So I'm an associate professor in computation catalysis. This is my main area, but I also have group members that are doing experiment because I think it's very important that theory and experiment work together in order to understand chemical mechanisms. And I will come back to some of our joint studies. So I will just proceed. Please interrupt me if there are any problems with the slides or with the sound. I have a brief outline here of my talk today. I wanted to just give a few words about our university. It's the northernmost university in the world. So many of you may not have heard about it even before. And I will also introduce my group a little bit. Then I will tell you a bit about computational catalysis. I think perhaps many of the people in the audience are actually experimentalists, so I will just give you some background. And then I will present to you some of our work on hydrogenation and carboxylation reactions. So if we start with the university, that was the original name. We recently changed name to UiT, the Arctic University of Norway, so that everybody realizes where we are located. I don't know if you see my pointer. I will just change it. So I hope you see my pointer. We are in Tromsø. It's above the polar circle here in northern Norway. And what you see here on the right side is a picture of the island where we are located. So the university is actually on an island. There's a red arrow pointing towards the university. Right now, it's the dark times. So it's permanently dark outside. And under those conditions, we can see the northern light. We have a picture down here. You also see some of our mountains with the snow on top. And then we have a picture here from our campus. This picture was taken in the summer. In the summer, it's actually permanently light here. So it's complete contrast. The sun never sets for 2 months. At the university, we have around 4,000 employees and 16,000 students. And this university, as I said, is the northernmost university in the world. And it covers all areas of science. So it's what we call a broad university in Norwegian. So it doesn't focus on specific topics, but it tries to do research in all relevant topics of natural science and social science. So at this university, I lead a group which is called the CHOCO group. CHOCO stands for Catalysis for Homogeneous Conversion of CO2. We are located at the Department of Chemistry. You see here a group picture of some former and current members. At least one of them may be familiar to you. So Jana Kirim used to work in my group some years ago. On the left, what you see here is a picture of our supercomputer where we run calculations, and I am responsible for all the work that is being done computationally. We also have another associate professor in the group, Associate Professor Annette Bayer, and she's an organic chemist, so she is main responsible for all the experimental work that is being done. You see some of our experimental equipment here. This balloon contains CO2, actually. So what we try to do is we try to model systems on the computer and then also do experimental studies at the same time. So for me, computations are just an additional tool, like you do an NMR or you do an MS, some additional equipment that helps you to gain insight into your system. I think computations should never be completely alone. You should always have some other information about the system, because the problem is that if you only do computations, it's actually quite hard to know all the things that are happening in your reaction tube, or in doing the reaction, especially for reactions in solvent. Very many things may happen, and it's quite important that you already have some insights before you start building your model. But I will come back to that. So my research profile is such that I focus on analysis and design of metal-catalyzed reactions. I really love metals. This is probably also part of the reason why I have become an associate editor for organometallics. I also lead 2 consortia. One is a European consortium. It's a so-called innovative training network on CO2 conversion. It combines both experimental and theoretical and industrial groups developing CO2 conversion reactions. And I also lead a Nordic consortium for CO2 conversion. And this is an association between 9 Nordic universities that together are developing new CO2 catalysts. So we have again computational and experimental people, and it's different types of chemistry. So some do homogeneous catalysis, some do heterogeneous, photo. There are various types of groups involved in these consortia. And I put the websites here for those that may be interested. We regularly have open positions also in these consortia, so maybe I will meet one of you there today. I have a few selected papers here at the bottom. It's not so important, just get an idea. Now I wanted to say a few words about computational catalysis. So computational catalysis is a topic that is growing. One of the methods that is being used a lot in computation catalysis is so-called density functional theory. This is an electronic structure method that is being used to describe molecules. The abbreviation is DFT. And if you do a search on Web of Science for DFT and mechanisms during the last 20 years, this is what is coming up. So from around 160 papers in the year 2000, we are now at 3,500 papers. So it has increased by 20 times in 20 years, and I think it's going to increase even more. So methods are getting better. More people have access to computational methods and to supercomputers so that they can do calculations on large systems. So I'm certain that this area of research is going to grow tremendously. And then there are also additional overlapping areas such as machine learning, artificial intelligence. When this is combined with computational catalysis, one can really study very many systems fast and make good predictions. So there's no question that in silico chemistry is going to grow. But the question is, how meaningful is really computational chemistry or computational catalysis? And I like this quote from 1987. It's by a late professor of chemistry, Peter Hopmann. And he wrote in an article, "We still have a long way to go until a computation will be able to compete with or to substitute a lab experiment. From a very pessimistic standpoint, experimental chemists sometimes tend to adhere to this opinion. One could then conclude that theoretical work in this field, not being quantitatively reliable anyhow, is rather useless, except for the purpose of keeping theorists busy." So we have to remember this was written in 1987, but I am afraid that there are also people today who think like this about computational chemistry. But if we go back to how was it really in the 1980s to do computational catalysis? So imagine you have a reaction in solvent. It's a metal complex, for example, that is supposed to react with an incoming substrate, and you want to describe the system with computational catalysis. If you wanted to do this in the 1980s, then your options were really limited. There were not yet any models to describe the solvent, so you can only describe the complex. Most of the complexes were too big, so you could not actually compute them, so you have to truncate them. You could not yet do a geometry optimization of a system containing a metal, so you would have to fix the geometry, the coordinates, based on a crystal structure. And the methods that had been developed at this time, they were not yet able to describe electron correlation. So that is the way how electrons affect each other. And this was not yet fully described at that point. So the methods were highly inaccurate. So this is the situation in the 1980s. Still, people were able to look at chemical systems, make predictions, explain some of the reactivity, but it was quite limited compared to what we can do today. So if we look at what is possible today, I would say that we can pretty much model now this almost complete system. We still have to make significant approximations, but we are at least trying to include all of the effects. So for example, the effect of the solvent and the effect of the full catalyst in the calculations. So people can now compute up to 200 atoms without huge problems. It's important to mention that the type of calculations that people do when they run ordinary density functional theory, this is static. So that means dynamics. So how the system evolves over time is not really included. But what people do is that they optimize conformations and get an energy for those conformations, and then they can compare different conformations and say which one is more likely, for example, get a Boltzmann distribution of conformations. Then it's possible to model the solvent. Now there's a problem. If you include very many solvent molecules, they have a lot of freedom, and it's really difficult to model that with a static system because you would have every possible conformation of the solvent you would have to take into account and then average over all of them. And this is much too time consuming and difficult to do. So therefore people have developed so-called implicit models. So they model the solvent as a homogeneous continuum, that is polarizable. And then there are some parameters given to the solvent. So the dielectric constant, which you see here in epsilon, and R is the radius. So this corresponds to the radius that the real solvent molecules would have had. And these parameters help this implicit solvent model to make a cavity. And so, for example, the size of the cavity is determined to some extent by the radius of the solvent. So how close can the solvent actually get to the molecule that is inside the solvent, so our solute here. And sometimes people include a few explicit solvent molecules, for example, when they know that those solvent molecules are participating in a reaction mechanism, for example, by binding to the metal complex or by being reactive members. There are very many density functional theory methods. There's a so-called Jacob's ladder. If some of you have experience in this field, you may have heard that term before. And it starts with the so-called Hartree-Fock method, which was pre-DFT. And then DFT sort of builds on top of that. And there are very many different functionals, and they increase in accuracy. So the idea is if you go along this ladder, at some point you will reach a method that has chemical accuracy. And what we define as chemical accuracy is if the error between your computed value and the experimental value is less than 1 kilocalorie per mole. So this is sort of what we aim for. This is our so-called chemical heaven, if we manage this kind of accuracy. And I think this is possible with many methods. The main problem that people have is that they often do not know in the beginning which method to choose because different methods have different strengths. And you cannot know if this particular method you have chosen will have this kind of accuracy for your system. So there's a lot of ongoing work in this field where people are benchmarking functionals to understand which systems they are good at describing, and also to develop protocols that should help people choose what is the best functional for their system. So there's one particular problem in density functional theory. It's that it's not very good at describing so-called dispersion interactions. So if you imagine two benzene rings, and if you would run a geometry optimization on these with a computational method that does not include any dispersion corrections, they would actually move away from each other. But this is physically not correct. There should be a dispersion interaction between them. So they are like induced dipoles on each of these, which lead to an interaction. But dispersion corrections have been developed, and they are typically added on top of the DFT, and they then give the correct physical behavior and also much better energies. I did a benchmark a few years ago. Here, these are names of different functionals you see here, and the arrow, this is the arrow for 11 reactions I computed, iridium-catalyzed reactions, and this is in kilocalories per mole. So there were actually some combinations. So this is, for example, the so-called PVE functional with a D2, so dispersion 2 correction, that gives arrows for those 11 reactions of around 1 kilocalorie. So this is really promising. So in principle, we can say that we now have the methods that are good enough for computational catalysis. So this is a cover that I designed at the time. You see here the development of different computers and also different models. So we can say we now have the methods, and we can actually study quite complex reaction mechanisms. This is a reaction mechanism that one of my PhD students studies. So we have many steps. We have substrates and solvent molecules and various things coming in and out of the reaction. But we have to ask ourselves, if we use these methods, do they automatically mean that the mechanism we are going to compute is actually going to be the so-called correct one? I think we should be careful to call a mechanism correct. We can never be certain, not even when we do experiment, that we have found the correct mechanism, but we can arrive at a mechanism that does not disagree with any of the experimental findings. And I call that a validated mechanism. And I think that there's not enough focus, unfortunately, often when people do computational studies, that they are not sufficiently attentive to make sure that they do not only use a good method, but they actually critically evaluate the results that came out. I wrote an editorial about this last year for some of you that are interested. So here are some insights on how I recommend to structure a computational paper, but also about the importance of validating the results. So how can you validate a computed mechanism? And I think you can always ask yourself some control questions. So, for example, was the model and the method you used meaningful? you have to look at benchmarks, for example, for the method. But for the model, it's often very important that you actually compute the full system and don't truncate it as people have a tradition to do. You can look at the barrier. Is it actually feasible at the experimentally known temperature? There was a very nice tutorial in 2018 by Bike and co-workers, and they go through different pitfalls in organometallic computational chemistry. And they also give some insights, like what is a feasible barrier. So for example, if you have a room temperature reaction, your barrier should not be above 25 kilocalorie. That is too large for that. You would actually not produce sufficient amount of product. It cannot be a reasonable barrier if you go higher. And then what is very important to me is our experimental substrate preferences and selectivities. Are they actually reproduced by the mechanism? And the only way to know that is if you actually study more than one substrate. So I wanted to show you some examples from our laboratory. Since I primarily work on hydrogenation and carboxylation, these are, of course, from these two areas that I represent to you examples. So if we begin with metal-catalyzed hydrogenation, it's a very interesting field. The first homogeneous hydrogenation catalyst was already reported in 1938. It was based on copper, and there has been a lot of work since then, and of course a lot of development of asymmetric reactions as well. So this started in the 60s and 70s. So I cannot go through all of these, but for those of you that work in the area, you have probably heard many of these names before. Here are some of our papers on hydrogenation. We have mainly worked on iridium and I see that cobalt and iron. Yes, these are the three metals that we have mainly worked on. And we have worked in this area for approximately 10 years now. Here you see a cover that I designed a few years ago, where you see how a chiral acid sort of puts itself around the reactive center, and in that way governs the energy selectivity of the reaction. So the first example I wanted to present to you is an experimentally known system, an Iron-pincer system that is able to hydrogenate ketones and aldehydes. And it's mild reaction conditions, so at room temperature and low pressure of H2. The system was reported by Kirchner and co-workers in 2014. And here are some of the substrates that they studied. So they studied, as I said, both aldehydes, but also ketones and different types of substituents on the ketones. It was quite interesting to see that aldehydes actually had less reactivity than ketones. That's sort of counterintuitive chemically. So immediately one can get interested to see if there's a mechanism that can explain that. There was a proposed mechanism. Here you see it. It's an insertion mechanism where you have the iron complex with the hydride, the substrate binds, the substrate inserts into the iron hydride bond, then another H2 molecule coordinates, and a proton is being transferred, and you form the product. And there were some computations reported on this small substrate here. So I call this a model substrate because this was not actually tested in experiment. And the computed barriers were very reasonable. Oh, I see my pointer starts painting here. So around 17 kcal. But what we were interested to understand is if this mechanism could actually explain the substrate preferences that were seen in experiment. And if you think that there's a correlation between the rate of the reaction and the yield that you get, then based on the yields that were reported, you would expect that there should be a small barrier difference between these substrates. And this work was done by my previous postdoc, Dr. Cloyne Morello. And for those of you that are computation chemists, you see our method here below. For those of you that are not, doesn't matter so much which method we used. But we tried to use a good method with dispersion corrections, a large basis set, and also solvent effects. And we did full models. And what you see here is the rate-limiting hydride transfer of this proposed insertion mechanism. And here are the barriers for two of the substrates that are known experimentally. So two things you should immediately notice. One is that the barriers are very high. So this was a room temperature reaction. You should expect a barrier that is around 25 or below, but the barriers are much larger. The other thing to notice is that for these two substrates, there's a very large barrier difference of more than 14 kcal. But based on the experimental results, we expected around 1 kcal. So this leads to the conclusion that this mechanism most likely is not the correct one. So what do you do in such a situation? You go back, you look at what has been reported, for example, experimentally, what kind of intermediates have been observed. There's a dihydride intermediate that has been observed for this complex, and also for a related complex, there's an alkoxide intermediate that has been reported, and there was actually a paper already in 2011 predicting that these intermediates could be part of the mechanism. So we formulated a new mechanism that starts from the dihydride, and the substrate doesn't actually bind to the complex. It's in the outer sphere. You transfer a hydride to the carbon of the carbonyl, and then you develop a negative charge on the oxygen. Now this compound has strong affinity for the metal, so the alkoxide binds quite strongly. It can now abstract a proton from the backbone, and you form your alcohol product. But now you need to regenerate the catalyst, so H2 binds. And then it's quite hard to transfer a proton from H2 to the backbone. But if you let, for example, a substrate molecule or a solvent shuttle this proton, then the barrier is quite low. Here you see the transition state. The barrier was 20.2 kilocalories for the whole cycle. And in this way, you now here reform the active species. So now what is really interesting for us to do then is to do many substrates. So here you see 5 different substrates, different colorings, and this is the computed reaction profile based on the mechanism that I just showed you. And what you see here is an interesting behavior. So for example, the benzaldehyde, which is expected to be most reactive, indeed, in the first step is the most reactive substrate. So this is based on chemical intuition, that one would expect an aldehyde to be more reactive than a ketone. But in this particular reaction, the aldehyde is actually not more reactive. And the reason is that the aldehyde forms a more stable alkoxide intermediate. So that in the end, the overall barrier, if you go from the lowest state to the highest state, the overall barriers for these different substrates become quite similar. So here you see the values in kilocalorie per mole. And what you can see, all 5 substrates that were experimentally active have feasible barriers, and the barriers are close. So we expected a barrier difference of around 1 kcal. What you see here is a difference of 1.8 between the 5 barriers. So this is within what we can expect, the error of our methods. So this provides support for the dearomatization mechanism that we have proposed. I want to present you a second hydrogenation example. This was cobalt-catalyzed hydrogenation, and now what you hydrogenate is not a ketone, but an alkene. And again, you have relatively mild conditions, room temperature, 4 atm of H2. This is a system that was reported by Schirik and co-workers in 2014. What is really intriguing about this system is that if you take almost the same substrate and you either put an hydroxyl group or a methoxy group, then the methoxy group leads to very little conversion, and the hydroxy group leads to large conversion. And this was shown for several substrates. So the substrate needed an alcohol group in order to show good conversion. And what is really intriguing is that if you look at the 3 examples given here, the alcohol group is placed relatively far away from the double bond. So it's not clear what is its function. But you see the same trend for all of these 3 substrates. And for one of the substrates, it was also reported a diastereomeric ratio. So when you look at this substrate, it's a 6-membered ring, so it will form a chair conformation. We have 2 substituents here, the methyl and the isopropyl, and they can either be on the same side in the product or they can be on opposite sides. So that gives the so-called cis and trans products. And you see there's a huge reference for cis, even though actually trans is energetically lower in energy if you would just compute the 2 products and take the energy difference. So that's interesting. There was a proposed mechanism, a redox mechanism. It's quite similar to the redox mechanisms that are known from rhodium-catalyzed hydrogenation reactions. So you have an H2 molecule coming in, doing oxidative addition to cobalt. So you go from cobalt 0 to cobalt 2. The substrate comes in and binds. A hydride is transferred. So you form this alkyl species. This alkyl can now abstract a proton. The electrons here go back to the metal, and we are back at cobalt 0. So this mechanism was previously computed with full substrate and showed reasonable barriers. So there's nothing here that sort of disagrees with the experiment. The only thing is that the mechanism doesn't actually provide any explanation for the role of the OH group. So why do substrates without OH groups not? Why do those substrates not work? This was something that we were interested to understand. So again, Glenn, my previous postdoc, looked at this system. He chose two substrates, one with a methoxy group and one with an alcohol group. The reason we chose those is because for this alcohol substrate, there was also a reported diastereoselectivity. So that means we have two things we can check with our mechanism. We can check the substrate preference, so the alcohol substrate should be preferred, and we can check if the computed mechanism can predict the correct selectivity. Down here again, you see our computational protocol. So if we first take the proposed redox mechanism, what we found out is that the two substrates had essentially the same barrier, even though in experiment one substrate would be hugely preferred. So this was not in very good agreement. And the second thing we found for this proposed redox mechanism is that the diastereoselectivity was not correctly described. So even though there was the right trend, the mechanism predicted about 75% of the cis, while in experiment there should be more than 99% of the cis product. And if you convert these percentages into kilocalorie, it's actually several kilocalories per mole in difference. So this was an indication to us that this mechanism may not be correct. So we thought for a while, so what can you do with a substrate that has an OH group? You can potentially deprotonate it. So imagine you can form this group. I will come back to how it is formed, but imagine that this is actually the proton that was previously on this oxygen, but it has become a hydride. And then you can transfer that hydride to the substrate, and you can form a so-called metallacycle. Here you see the transition state for formation. So what we noticed is that the metallacycle was low in energy, making it quite likely that it could be formed. So we developed a mechanism that involved this metallacycle as an intermediate. So we start from a so-called monohydride, that is where the substrate is deprotonated. I will come back to how this happens. The hydride is being transferred. We form this metallacycle intermediate, H2 comes in. Now we have sort of a formal negative charge on this carbon. It can abstract a proton. Now we have hydrogenated actually the substrate, but it still has an O- here. So what can happen next? A new substrate comes in, and the product now steals a proton from the substrate, and in that way we have formed the final neutral product, and we have reformed this species. And the overall barrier for this mechanism was very feasible, 21.3. So what you see here is the energy profile for the redox mechanism versus the metallacycle mechanism. So in blue and orange, this was the originally proposed redox mechanism. You see relatively higher barriers than the metallacycle mechanism, and you see that the two different substrates here, R equals hydroxyl group or R equals methoxy, they have almost the same barriers, indicating that there should not be a preference for one over the other. But if you then go to the metallacycle mechanism, this mechanism is only accessible for the hydroxyl substrate. So the other substrate can actually not access this mechanism. It has low barriers, and you see the difference here. So 21.3 for the hydroxyl substrate via the metallacycle mechanism, and with the redox, it would become 32.6 if you start at the lowest point and take the barrier from here to the highest point. So there's no question that the metallacycle mechanism is preferred. And if you look at the selectivity, now the barrier is much lower for the hydroxyl substrate in agreement with experiment. And if we look at the diastereoselectivities, actually we predicted 100% of the cis form should be formed. This has something to do with how the substrate binds to the metal, that the hydride transfer could happen from one side. And this is very much in line with what is observed experimentally. So then when we had found this mechanism, we teamed up with the experimental group that has previously reported the system. So Sherik's group, and he has a student in the lab, Aaron, and we asked them if they had any idea what kind of experiment we could do in order to have support for our proposed mechanism. So they came up with this experiment where they have they take the pre-catalyst and they mix it with substrate. And then what they see indirectly through NMR, they see that one of the groups on the pre-catalyst is cleaved off, so it's protonated. And then they have, this gives them an indication that there most likely is an alkoxide that has been formed. And then they add some TMSI and they see a reaction between what they think is an alkoxide, and so it binds to TMS. So this indicates that there is actually that this system can actually result in formation of an alkoxide intermediate, and this is what we predicted as part of our reaction mechanism. So both the experiment and the computational results, I would say, validate that the metallacycle mechanism could be correct. But it's important for me to come back to that there's no way of ever knowing that you have a correct mechanism. The best you can hope for is that your mechanism doesn't disagree with any knowledge that there's current about this system. But one should always be prepared to revise a mechanism. So then I wanted to give you one example from metal-catalyzed carboxylation, which is the other big area that we are working on. We have worked in this area for around 4 years. There are many other people working on homogeneous carboxylations. I have given some of the seminal names here for those working in the field, you may know. And it's also important to know that CO2-based carboxylation reactions have already existed for a long time. There's a lot of hype in this area, so people are trying to sell CO2 as a potential starting material in chemical synthesis. I'm also one of those people because I think it's a very promising synthetic starting material, but it's important to know that this is not a new idea. So this has work in this area has been done for a long time. And one of the people that is working in this area is Professor Walter Leitner. And already in 1996, he said that the understanding of how CO2 is activated in a certain reaction is not of mere academic interest. The search for new reactions involving CO2 as an environmentally friendly and economically feasible source of carbon can only be successful if we understand the underlying principles of CO2 activation. So this is a very interesting area. CO2, as you may know, is not flammable, it's inert. It's actually the highest oxidation state of carbon, so it's quite hard to make it react with anything. So the idea is that if it interacts with a metal, it can be activated and you can make it interact with another substrate. But then it's very interesting that there are very many reactions where it looks as if the CO2 is actually not interacting with them. So this is something that we became very interested in and started working on. So the areas that we work on is all homogeneous CO2 activation. There's also a lot of work on heterogeneous CO2 activation out there, but this is not our area. And we are very interested in selectivity. So if you do a search on SciFinder and look at the reports, was a search from 2019, how many CO2 reactions there are that actually involve an enantioselective reaction. It's very, very few. These are the red bars here. So this is an area where not so much work is being done, partly because it's very complicated to make enantioselective reactions. If you think about asymmetric hydrogenation, it took probably 20, 30 years before you had very good asymmetric hydrogenation catalysts. And I think the same will be the case also for carboxylation reactions. But if you want to use CO2 as a chemical starting material in academia or in industry in the future, you also need to develop enantioselective reactions. There's no question about it. So somebody has to do it. So we are not really there yet, that we have developed many of these reactions. So we are still at the stage where we are investigating how carboxylation systems behave. So I wanted to give you an example here. I first mention a few of our papers. We have mostly worked on rhodium, copper, and nickel, but also on cesium a little bit. And I was editor of a special issue in organometallics this year. For those of you who are interested in sort of the state of the art in the field of organometallic CO2 activation, you can have a look. So if you go to the organometallics website, you should find a link to all of our special issues. And what is really interesting here, as I said before, is to understand how CO2 is being activated. So there was an idea that the activation of CO2 must occur through the metal. But already in 1996, Professor Leitner again said that theoretical and experimental work suggests that only weak interactions between CO2 and the active metal center are sufficient. What we would like to propose based on computations is that there are many centers where there are no interactions whatsoever, not even weak. And there are also other people in the field who have made similar observations. So we try to divide carboxylation reactions in sort of two camps, inner sphere and outer sphere. So you have interactions in inner sphere, but not in outer sphere. And I wanted to just quickly give you at least one more detailed example. So we are interested in group 9 to 11. So we have worked with rhodium and nickel and copper, which are from these groups. And here is a rhodium system that we have investigated. This was originally reported by Mikami in 2016. This was the first system that could do an in-antiselective hydrocarboxylation using a rhodium SegPhos system. And these are the type of substrates that could be carboxylated. And you see the yield is moderate and the E is also moderate with SegPhos. If you use COD, you get much higher yield, but of course COD is not chiral, so there's no selectivity. Here, the reported substrate preference, you see that if you have an ester in the substrate, then it's reactive, but if you have an amide, then it's not reactive. This was one of the things that we thought was interesting to potentially model. Here's a proposed insertion mechanism where you form a rhodium ethyl. You have zinc diethyl in your soup, and this is responsible for forming this rhodium ethyl, which can undergo a beta hydride elimination, so you form a rhodium hydride. You can insert the substrate, and then you form this alkyl intermediate, CO2 can insert, and you form the carboxylate, which then transmetallates, so you are back to start. This was the mechanism proposed based on experiment. So we looked at this both experimentally and computationally. You see some of the people involved in the work. So Liliana was my previous PhD student who did the computations. And here you see Dr. Jana-Kiran Weitler, who was doing the experiments on this system. And Annette is the associate professor in organic chemistry who was involved in the experimental work. Here again, you see our computational protocol. So what we expected initially, based on reports in the literature, is that CO2 would interact with rhodium and that the transition state would look more or less like this. What we found is that it looks completely different. So here you see the substrate coordinated to rhodium. So this is at the carboxylation step. And you see that the carbon that is supposed to interact with CO2 is far away from the metal, actually. And the CO2 has absolutely no interaction with rhodium. Here you see the barriers for the two transition states. So there is no question that this outer sphere transition state with a barrier of 14.4 is very much preferred. This reaction is supposed to happen at 0 degrees. So then you want a small barrier. Here, the inner sphere is 37.9 kilocalorie per mole. So it's absolutely not feasible. Then we looked at the two different substrates we were interested in, and you see here that on the right side is the ester that had the 14.4 kilocalorie, and on the left side is the amide, which had a much higher barrier, 5.4 kcal higher. This barrier is still feasible under the reaction conditions, so we think that it's probably underestimated, but just the difference between them gives you an indication why one of them is active in experiment and the other not. Finally, we looked at the selectivity. And we did that with SegPhos as the ligand. Again, inner sphere barrier for carboxylation is much higher than outer sphere. Here you see the two variants. So the two barriers we got for S and R. The difference is 1.2 kilocalorie per mole in favor of S. And this is what you would expect based on the experiments that were reported by Mikami. You would expect about 0.8 kilocalorie per mole in difference. So we are quite close to that. Then we also did some experimental studies in order to further support the mechanism. So this work was done by Jana-Kiran, and he managed to see the rhodium hydride, and he also showed that during the conversion of the substrate, he showed that he has good support for that this intermediate actually is formed. If he does the reaction in absence of CO2, then he sees a dimerization of this one. But in presence of CO2, we form the product. So together with these results, we the experimental and computational results, we think that for rhodium, there's an outer sphere mechanism for CO2 insertion. And since we also managed to reproduce the previously observed selectivity, we are quite confident that this is the correct mechanism. But now what we're interested in is to see if other systems that also have a similar type of substrate, so a benzylic substrate, if they also behave in the same way. So in total, we have now computed 4 examples. The first one was the rhodium system that you just saw. And there's no question that the outer sphere transition state is usually preferred. So rhodium is from group 9. And the inner sphere one is 23.5 kilocalorie higher in energy. If we now go to the next group, so look at palladium. This was worked on by my previous postdoc, Diego. He also studied inner sphere and outer sphere transition states. You can see again the substrate has this interesting binding mode in the outer sphere transition state. So it's the ring that actually binds to the metal, and CO2 is coming here in the outer sphere. And the barrier of the outer sphere is 7.4 kilocalories lower than the inner sphere. So again, there's a strong support for an outer sphere mechanism where CO2 doesn't interact with palladium at all. Then we looked at copper. My previous PhD student Mark looked at a copper reaction, and you see the outer transition state here and the inner. And here the energy difference is only 1 kcal. Still in favor of outer, but it tells you that copper behaves differently. We tested a second copper system that was worked on by Diego. And here we again see that the barriers are similar. And if we change the ligand, so if we go from IPR to IMS as NHC ligand, then there is an inversion in the preference. So with IPR, the outer sphere is preferred, but with IMS, actually the inner sphere is preferred. So if you work on copper and you do carboxylation reactions, you must expect that both inner and outer can happen. And this is really important if somebody wants to develop in anti-selective reactions, because these two modes of attack would give you opposite configuration. So I just want to end with saying a few words about trends, because ultimately what you want to see trends, because trends allow you to also make predictions even before you did computations on how your system most likely is going to behave. So we have looked a lot at benzylic nucleophiles, but if you look in the literature, you can also find information on other types of nucleophiles that undergo carboxylation, and it's possible to group these. And we have done this, but there's also a very nice article by Hazari and Hopmann where they have looked at different systems and tried to group them based on their behavior. And then you see that if you have alkynes as your original starting material, or if you have benzylic carbons, then you can expect outer sphere transition states. If you have sp2 carbons, you can always expect an inner sphere. That is quite interesting. We have done a lot of studies that I don't have time to show you today. It's always inner sphere. And if you have a non-benzylic carbon, it's most likely inner sphere, but there are some exceptions. And you can actually relate this trend to the pKa. So this is what Hazari has proposed, that there's a correlation between the so-called nucleophilicity, which is then related to the pKa of your nucleophile, and the likelihood of having an inner sphere and outer sphere reaction. So if you have a high pKa, it's more likely that it's going to be an inner sphere reaction mechanism. But there are some outliers. I want to just show you one. So for palladium and nickel, when they react with, for example, a methyl, then it seems to be outer sphere, even though it's a non-benzylic carbon. And we are at the moment trying to understand and model some of these systems to see what the reason could be. So my conclusions. I believe that static DFT methods have reasonable accuracy for computing mechanisms of transition metal reactions, but I think it's very important to be attentive to barriers, substrate preferences, and selectivities. If they do not agree with experiment, then perhaps the mechanism may be wrong. And then I have showed you some examples of hydrogenation and carboxylation reactions we have done, and giving you some insight that it's not, it can be very unusual hydrogenation mechanisms. It doesn't necessarily have to be a conventional redox pathway. And for carboxylation, you should expect that, especially for benzylic carbons, there may be an outer sphere insertion happening. I want to, this is my take-home message visually. So please validate your mechanism. Otherwise, it's just an apparent mechanism that you cannot trust. And I want to, at the end, just thank our collaborators, our funding agencies, and of course, the members of the CHOCO group. So in bold, you see those that have done the work that I presented to you here today. So Liliana and Mark were my previous PhD students. They are now continuing in the group as respectively postdoc and researchers. And then, of course, Annette and Ashot, who have been involved in the experimental work, and some of our previous members who have done the experimental and computational work. And finally, I just want to remind you about our fantastic journal, Organometallics. So we are inviting contributions about all areas of organometallic chemistry, also hydride chemistry. So hydrogenation is a big topic, and I'm the computational person on the team. But we hope to see more papers also from India on experimental and computational chemistry. So I would really be happy to handle some of your submissions. So that was all from me, and thank you for your attention. I will try to.
Thank you, Kathrin, for insightful and thank you, Kathrin, for the insightful and stimulating talk. I hope many students and faculty enjoyed your talk and understood how computational methods are applied to investigate organometallic reaction pathways. Asymmetric carboxylation using CO2 is a really challenging task, and it is very important also. I think the calculations of what you have shown, like inner sphere transit and outer sphere, those can help experimental chemists to formulate new concepts in asymmetric like carboxylation reactions. It's a very interesting talk, and Professor Soumik will take over question and answer session. And over to you, Soumik.
Thanks, Janaki, and thanks again, Professor Kathrin, for the excellent talk. And should we take some questions now? There are a few questions. Professor Kathrin?
Yes.
Okay, sure. So,
yes,
so we had been like streaming this on YouTube. So there are a few questions from YouTube, and there are a few questions through personal chat also in Webex. So I'm just going to ask them. So there is a question from YouTube which asks like, since all the reactions are mostly done in solvents, so do you also simulate solvents in your simulations? Like, do you include solvents in your simulations? That's the question.
Yes, this is an important question. So we do simulate solvent effects, but we do this through modeling a continuum. So that means we do not have real solvent molecules. For example, if the reaction is in ethanol, it's not a real ethanol molecule there, but there's a medium around the molecule, like, for example, the catalyst. And this medium has the same properties as the solvent. So it has the same dielectric constant. We are not able to fully model each individual solvent molecules with like static DFT, but there are developments in the field. So for example, those people that do molecular dynamics, they are able to run really the explicit solvent. But in all the work that I showed you today, it is implicit solvent models, meaning that there's a continuum that has the same properties as the solvent. For example, it stabilizes charges. This is quite important. Very often in organometallic reactions, you have a charge developing at one of the centers, for example, on the substrate. And then this implicit model is able to stabilize the charge and give more correct energy than if you would not have it there.
Okay. Okay, so the next question is from Vikas. So he asks like, what software do you use for the simulations, or do you write your own codes?
This is a very good question. Yeah, I'm sorry if I didn't mention the software. So we do a lot of work with Gaussian. We also use a different software that is for free called Ochre. That has some very nice features. And then we also at our department are developing new methods. All of the work that I showed you today was done with Gaussian, if I remember correctly. But some of the future work that we are about to publish, we have run calculations with some of our local software. So we have local collaborators at our department that are developing new methods that we are testing. So this is a continuous field. We are all the time interested to also test new methods to see how well they behave for metal-catalyzed reactions.
Okay. Okay. So the next question is like, so you can predict the reaction mechanism, but can you predict the yield of the reaction by simulations? That's a question.
This is a very good question. I think the short answer is no. But if you think that there's a correlation between the yield and the barrier, so what we can predict is the barrier, and we can predict the reaction energy. So the reaction energy tells you something about how favorable this reaction is, and the barrier, how fast it is. So based on these, if you have these variables, if you have computed these parameters, you can say something about if this reaction is going to happen or not. But the exact yield you cannot predict, because the yield is also dependent on other factors such as solubility, which, you know, when the final yield of an experiment also depends on how did you actually isolate your product. So maybe you moved it from one solvent to another solvent and so forth. So this is not something that we can predict as of today.
Okay, okay. So some more questions coming in, but I'll just choose a couple of them only. So the next question is, okay. So do you see a future where computational techniques can completely replace experimental trials? Okay.
Again, the short answer is no, I don't. I think
Okay.
some people believe that, yes, but I think that we can teach the computer a lot, and people are now using artificial intelligence and machine learning to try to teach computers to predict mechanisms. But I think you will always need some intuition in order to understand chemistry, and this comes from experiment and from experimental results. And also, I think what is the ultimate goal of chemistry is to make products, and we cannot do that with computations. So we can use computations to explain chemistry, but we cannot actually do chemistry with computers.
Okay, okay, okay. So probably the last question of the day. So what are the most challenging reactions that can be studied computationally?
That is a good question. So you can, it depends on what you mean with challenging. So some systems are challenging because they are large, but that as long as you have computational power available, that is okay. So from my perspective, the most challenging systems are those that have a complicated electronic structure. So if you, for example, have open shell metal that can have multiple spin states that are close in energy, such as systems that are quite complicated, and people are using computational methods to study this, so this is possible now, but it's a little bit of what I would call at the edge of what computational chemistry can do. So I don't think that our methods yet are fully good enough to study these systems in the detail that we would like to. So what I mean with that is we cannot fully trust the energies that would get out of it. So for example, if we say that for a particular system, a doublet spin state is preferred over a quartet spin state, we cannot yet be totally sure. So these are the systems that I hope we can describe better in the future. But when it comes to size, I think it's only dependent on the computational resources that are available to you. So we could do 300, 400 atoms without problems if we just have access to a large enough computer. So the methods are there to do that. It's more those systems that have a very complicated electronic structure. Those are still difficult to describe accurately.
Okay. Okay, so I don't see any more questions. So if there are no more questions, I would like to thank Professor Kathrin again. And yeah, over to you, Janaki. Janaki, are you there?
Thank you so much. Yeah, I'm there. Yeah, thank you so much. So once again, I'd like to thank Professor Hopmann for taking some time out and agreeing to give this webinar for faculties and students. And Kathrin, we would also like to host you physically in our institute sometime once this COVID crisis gets over. And a small information to the students. Our next talk of the series will be delivered by Professor Pablo De Vendetti from Princeton University, USA on 17th December at 6 p.m. Indian Standard Time. So the links to join the webinar will be available on our website, and the students are requested to register to avail for certificates. We will provide a special certificate to students who will attend at least 10 talks of this series in a year. Finally, I would like to thank Professor Anil J. Elias, HOD of the department, and Professor Ram Ramaswamy. He is giving excellent guidance for us to conducting this webinar series. And also, I would like to thank Dr. Somik, who is the main coordinator and the key person for this webinar, and also Dr. Bishwarup, who is a co-organizer. With that, I'm concluding this webinar. Once again, thanks to Kathrin and all of you. We hope to see you all soon. Have a great evening.
Okay. Thank you very much. Goodbye.
Yeah, thank you, Kathrin.
Thank you.
Thank you so much. It was nice seeing you, Janaki. Bye.
Nice to see you also. Yeah.